Alright guys, so today we're going to talk about the Lorentz force and the right-hand rule 1. Very simply put, it's the force a magnetic field has on a moving charge. But where does this come from? How does this force even happen? So I have this cute little charged particle, and if you recall from the section on magnetism, magnetism is caused by moving charges. And so when we have this ball right here. If we chuck that charged ball in through the air, that's a moving charge, and so it will generate its own magnetic forces, and those will interact with other magnetic forces, and that's actually what causes the Lorentz force. So moving charge, whee! This is the equation for the Lorentz force. You have a force is equal to QVB sine theta. Let's go through those variables real quick. I don't want to spend a lot of time because I have some other more important stuff to go over. So, force, F is force, and in the units are in newtons. Q is a charge, units are in coulombs. V is velocity of the object. That is the charged object that's flying through the air or moving, however, and that's in meters per second. And then B is the strength of the magnetic field that the object travels through. And that's actually in units of Tesla, which is the SI unit for magnetic flux. And that's one that's not commonly known and commonly used as much, but it is mentioned in one of the previous videos that another student made. And then our theta is the angle between the velocity and the magnetic field. And I'll go over theta a little more in depth, and that's going to be in degrees or radians. Just depends on what your calculator is using and what values you are given. So here's theta. Oh yes, my pen's working. So here's theta, well yeah, theta's up here. But what we're going to do is we're going to compare this velocity to this magnetic field. In this example, theta is pretty simply just 90 degrees, which is really interesting because when you have your force is equal to QVB sine theta, if theta is 90 degrees, sine theta becomes 1, and you don't even have to worry about that anymore. But sometimes it's not like that. And let's start over there. Sometimes it's like this. Sometimes the velocity and the magnetic field are not perpendicular to each other. And so F is equal QVB sine theta. You're going to need to keep that term in there. But just keep in mind, this is going to be your theta. One thing, I guess I'll go over in the next video on the right-hand rule, but the velocity and magnetic field lines are always going to form a plane, and you'll get to see that in just a sec. So right-hand rule 1 is pretty simply, I put these points on this slide here, these guys, just so you can write it down, but I made a video of myself so you can actually see what's going on. So let's clear that first. Okay, so the right-hand rule. The right-hand rule is a tool that we use to determine the direction of the Lorentz force. The Lorentz force equation tells us nothing about which direction this force is going to go in. That's why we use the right-hand rule as a tool. The way that they figured it out originally involves a lot of really complicated math that we're not going to be doing in this class. And that's why they came up with this nice and easy way to remember which direction this Lorentz force is going to go. Now there's two ways to do it. The first one, my favorite way, is you take your thumb, put it in the direction of the velocity of the charged object. So let's say we have a positively charged ball here. It's moving this way, so I'm going to put my thumb in that direction. And then let's say we have magnetic field lines going up. So my 4 fingers I'm going to put up in that direction. And they form a plane in both of our ways that we do the right hand rule, it's always going to form a plane, those two things. Sometimes it's going to be less than 90 degrees, kind of like that. I can't really do that. That's kind of hard. But even if it's less than 90 degrees, you're still going to be a plane here, and then whatever direction it is. So that's the velocity, magnetic field, and then the force of the Lorentz force is going to come directly out of my palm. So in this case, right towards you, the camera. So if the ball is moving this way, it's got a positive charge, magnetic field lines are up, then the ball is going to be pushed in a direction towards the camera. There's going to be a force in that direction. The other way, same thing for the thumb, it's the velocity of the ball, and then your pointer finger, instead of all four, your pointer finger is going to go up in the direction of the magnetic field line, and then your middle finger forms the force. Now one thing to be careful about is that's if this ball is positively charged, it works like that. The force would be going that way. If it's negatively charged, it's going to have a different interaction with the magnetic field, and the force is actually going to be out of the back of my hand. So positive is going to come out of the palm or your middle finger. Negative is going to come out of the back of my hand or the opposite direction of the middle finger.
Sweet.
Okay,
let's skip that. With that, the basic definitions, you got that down. Now we're going to work through an example problem. So, one day in the lab, you get angry and you chuck a charged glass rod at the wall. The rod, with 75 microcoulombs of charge, passes through a magnetic field of 3 Tesla, that's pretty big, at 30 meters per second. And that's a pretty good throw as well. What force does the glass rod feel and in what direction? So I made a little cute little diagram. There's you. You're like, what have I done? That's your glass rod, and you threw it. It's going there. You threw a magnet. Oh, yeah. So this is our example. And in this example, let's assume, the magnet's drawn like that, but let's assume the magnetic field's lines are going away from us, like that, except all up there. So what I'm going to do is I'm going to shrink that. There we go. And then work through this problem. So we're just going to write down our equation. So force is equal to QVB sine theta. And we have our information. We have 75 microcoulombs. We have 3 Tesla and 30 meters a second. And then theta is, we're going to assume it's 90 degrees from this equation, or this, I don't know how to say it, the diagram. There we go. So diagram. Force is going this way, and you have a velocity going this way. So these are perpendicular to each other. So theta is going to be 90 degrees, which means that's just going to be 1. So now all we have to worry about is force is equal to QVB. I apologize for my handwriting. I am not used to writing on screens. It's something I'm still learning how to do. So Q is 75 microcoulombs. We want it in units of coulombs. 1 microcoulomb is, well, 1 coulomb is equal to 10 to the 6 microcoulombs. It's like this little U thing. So I'm just going to go Q is equal to, well, that's force is equal to, but Q is 75 times 10 to the negative 6. Just make it 6 powers down. And that's coulombs. And then our velocity is 30 meters a second. And our magnetic field is 3 Tesla. I forgot to write meters a second here. And if you multiply all those things together, that gives us 6.75 times 10 to the negative 3rd newtons. Now these units, coulombs, meters a second, and Tesla, if you were to go through and do a bunch of algebra, you would find that these things do indeed equal newtons. So our force is 6.75 times 10 to the negative 3rd newtons for this problem. And now we have to figure out the direction though. So this is going straight to the right. I'm looking over here at this arrow again. So the velocity is straight to the right.
field lines are going into the page. So if I do my right hand rule, you can try doing this as well. So into the page is our 4 fingers, and then to the right. So we form like a horizontal plane, and then which means our force is going to be directly up. So our force is going to be directly up. Thanks, guys. So that's pretty much an overview of the Lorentz force and the right hand rule. I hope you enjoyed that, and I hope this helped you understand it. Have a good day.